Welcome to this explainer. Today we're going to be shrinking way down to the subatomic level. And I want you to imagine this invisible world as a massive, super intense, and perfectly tied game of tug-of-war. That's right, the chemistry happening inside literally everything around us, including you, can actually be understood as a perfectly balanced sporting event. But what happens when one side suddenly lets go of the rope? Well, we're going to break down exactly how atoms work, how they keep their balance, and what happens when they finally lose it.
Okay, let's dive into this. If we look at atoms in their natural resting state, they're completely neutral particles. They effectively have a score of absolute zero. But why is that? Why does an atom start out perfectly balanced when it's literally built out of particles that have electrical charges? And really, why should you even care? Well, because everything you interact with, the desk you're sitting at, the shoes on your feet, it's all built entirely out of these perfectly balanced games. To understand how they work, we really need to meet the players on the field.
So let's meet our two opposing teams. On one side we have the protons. These are our positively charged particles, and they're pulling hard in one direction. On the opposing side, we've got the electrons. These are our negatively charged particles, and they are pulling just as hard in the exact opposite direction. The entire game of atomic chemistry basically comes down to the constant push and pull between these two specific teams.
Let's look at the stats for the simplest game in the whole league, a hydrogen atom. If you count the players here, you get exactly one proton, so we put a positive 1 on the scoreboard. But look at the electron side. There is exactly one electron in a hydrogen atom, giving us a negative 1. Let's do a little math here, folks. Positive 1 and negative 1 completely cancel each other out. The positive and negative charges neutralize themselves entirely, resulting in a net charge of 0. It is a perfectly tied game.
Let's scale things up a bit and check the scoreboard for a carbon atom. If you count the particles here, you're going to find 6 protons, giving us a positive 6. But holding the line on the other side are exactly 6 electrons, giving us a negative 6. And just like before, the positive 6 and negative 6 cancel each other out. The game is still tied. This is exactly why we say an atom is electrically neutral. In its standard state, it always fields an equal number of protons and electrons.
Section 1. Losing a player. The sodium disruption.
All right, here is the story of the sodium atom. Step 1. We start with a perfectly neutral sodium atom. That means 11 positive protons pulling against 11 negative electrons, a 0-0 tie. But look at step 2. Let's say you provide sufficient energy to this atom. Maybe it gets bumped around or heated up. As a result of this sudden energy, it actually loses one electron from its outer shell. A player is knocked right out of the game. So moving to step 3, that perfect balance, it's completely shattered. The positive protons suddenly outnumber the negative electrons.
Let's run the new numbers. We still have positive 11 from our protons, but because we lost an electron, we only have negative 10 from our electron team. Positive 11 combined with negative 10 leaves us with a final score of positive 1. The sodium atom is no longer neutral. It's now a charged particle with a net charge of +1. The positive team has officially taken the lead.
Section 2. Catching the extra electron.
But wait, atoms don't just throw players out into the void. That knocked out electron has to go somewhere, right? Enter the fluorine atom. Before the chaos starts, let's check its stats. Fluorine starts as a perfectly neutral game. It fields exactly 9 protons and 9 electrons. Positive 9 and negative 9 cancel out. Net charge is 0. It's just minding its own business, perfectly balanced.
Now, what's really interesting about this is the dramatic catch. Remember that electron that the sodium atom lost earlier? Well, the fluorine atom swoops right in and gains that exact extra electron. Suddenly, an extra negatively charged player joins the fluorine team completely uninvited.
So, we have to tally up the new math for fluorine. We started with positive 9 and negative 9. But now, an extra electron has been gained, so we combine the positive 9 protons with the newly updated negative 10 electrons. The negative team totally overpowers the positive team. The math leaves us with a final net charge of negative 1. The fluorine atom is now a negatively charged particle.
Section 3. Cations, anions, and mnemonics. So, the scoreboards have permanently changed for both sodium and fluorine. They are no longer neutral atoms. This means it's time to bring out the chemistry rulebook and officially name these unbalanced atoms. In chemistry, any charged particle, whether it's positive because it lost an electron or negative because it gained one, is broadly called an ion.
Let me repeat that because it is absolutely crucial. A charged particle, either positive or negative, is an ion. So our unbalanced sodium is now a sodium ion, and our unbalanced fluorine is a fluorine ion.
But we can actually be even more specific based on which team is currently winning the tug-of-war. From our previous examples, we learned that ions can be positive or negative. The rule is simply this: positive ions are called cations, and negative ions are called anions. Sodium, which became positive, is a cation. Fluorine, which became negative, is an anion.
Now, I'm going to let you in on a clever little cheat code to help you never mix these two up on your next science test. And this brilliantly illustrates the difference. Take a look at the word anion. There are two N's in the word anion. You can think of that as 2 times the N for negative. Anions are negative. Now look at cation. There is only one N in cation, so it is less negative. And what is less negative? Positive. So cations are positive. It's a simple, perfect mnemonic to keep them straight.
Okay, let's do a rapid-fire recap of the rules of the balance game we've learned today. First, atoms are initially neutral particles because their positive protons and negative electrons are perfectly equal. Second, when an atom loses a negative electron, the positive team wins, creating a positive ion known as a cation. And third, when an atom catches or gains an extra electron, the negative team wins, creating a negative ion known as an anion. And by the way, these moving, trading ions, they are exactly what make up the electrolytes in your favorite sports drink, keeping your own body's electricity flowing.
So the crucial takeaway here is that atoms are constantly trading pairs to find stability. We've just looked at simple +1 and -1 trades today, but atoms can actually lose or gain 1, 2, or even more electrons depending on factors like their valency and their ionization energy. So think about this. What happens to the balance of power when a massive atom loses 3 electrons all at once? How violent does that game of tug-of-war get? Well, that is exactly what we'll have to explore next time. Keep questioning the invisible world around you, and I will see you in the next explainer.